Hello everyone, welcome to this channel and welcome to this video. I am Saptarshi Mukherjee. I am a software engineer 3 at Google and I am a competitive programmer. So in this video we are going to discuss the first 5 problems of the round that happened just 2 hours before, this educational Codeforces round 163. So there were many interesting problems out here. We are going to discuss the first 5 for today. Going forward, I'll actually try to plan some live sessions so that you can ask your doubts and we can discuss them, and that will make it slightly interesting. So the entire discussion shall be, in the direction it will align towards what your doubts are, where exactly your problems are, etc. But we'll plan that later. But for now, this is a quick editorial so that some of you who have recently given the contest can quickly see what the actual solutions are in case of some problems where you might have missed it. So yeah, starting with the first problem. So as you can see, I could solve 5 problems pretty early. I mean, in 1 hour 19 minutes. The first 4 happened in 40 minutes, and then I wasted some time. I lost some time over here in understanding the problem. Actually, I'll talk a bit about that. And F and G, I think they are interesting. I'll actually try to solve this F problem. I've had a look at it. There are some interesting aspects. I just got confused in some nitty gritty. Maybe in few days I might come up with this video. But okay, let's start with A. I'll keep this open to save our time. Yeah. So, the first problem, it says you're given an integer n. You have to build a string of uppercase Latin letters. There must be exactly n special characters. So the string is not of n characters, but there has to be n special characters. What is a special character? A character is special if it is equal to exactly one of its neighbors. So over here there are 6 special characters. Why? Because for the first A, you have one neighbor which is exactly the same as itself. This last A over here in these 3 A's, so basically this third A again is one such character which has one equal neighbor. This A is the third such special character. This A is another such special character. Then you have the 2 C's. Both of them are such special characters. So if I write down that string A, B, B, C, sorry, I missed something, B, and then double A, and then C, C. So what you see over here is this A says that yes, I have only one. This A says I have only one. This A says I have only one. This A also says I have only one. This C says I have only one neighbor which is equal, and this C also says I have only one, which means that in total we have 6 such characters. The tail of basically these arrows, we have 6 such characters which say that we have exactly one equal neighbor. Fine. Now what is the question? For n, we have to give such a string where that number of special characters is n. So if n is, let's say, even, then I think that the approach is pretty straightforward. For example, if n is 6, what we would just say is, if we have something like this, A, B, B, C, C, what do we get? We get something like this. For A, we have this A, and similarly, for A, we have this A. For B, this B, and this B will get this B. For C, this C, and this C will get this C, which means basically the moment I write the same character twice, let's say X and X, from here I get value 2. I get 2 special characters from here. After this, if I write, let's say Y, Y, from here I get another 2 special characters. So if n is equal to, let's say, 2k, then it is done. So I have to basically put A, then BB, then CC, and something like that. So I have to put same characters twice, and then some other character twice, then some other character twice, and so on. This is how it will proceed. So in any way I can do it. I can do it just with A, B, B, and so on. So for n equal to 8, maybe I can just move ahead with A and B. I can just say, okay, A, then B, B, and again either C or A or anything, any character. You can pick up Z also, Z, Z, and then any other character. Let's say the same B. Let's say we pick up B. so BB, something like this. So just that these two should not be the same, then it will take a different form. Okay, that is one thing. Now another thing is, okay, the string should be of length at most 200. Fine. So here we have used this kind of a strategy. Here we have used this kind of a strategy that for even n, the length will be n only. For even n, the length will be n only. We'll have the length n only. For odd n, what will we do? We have to keep within 200. So if n is 50, then for the even case, I'm not worried. The answer will be of 50 length or within 50 length. What happens if my n is odd? For that, let's understand a bit. How can I get some odd number? So let's say we have any number of a's. Let's say same character continuously many times. From this kind of a block, understand this, that before this, if you have some other character, let's say c. After this, if you have some other character, let's say x. There is no relation between them. There is no relation with that. There is no relation with that. So this is a completely independent block. This block gives you some special characters based on this own block. That x cannot get a special character due to this because there is a block of a's. So when it is about a, it is one block of a's that we are interested in. That can give us some special characters. Other characters would not find similarity with a, and a would not find similarity with other characters. So we want that equal characters as the first criteria to have special characters. So if I just focus on this block, that okay, from this block, how many can I obtain? This block and other blocks are all independent. That's what I tried to mention. So this block, how many special characters can it give me? So any block of a's, if I look at some middle a, which is surrounded by a on both the sides, I can say that for this the count is becoming 2. The question says that you can have, it should be equal to only one of its neighbors, not to 2 neighbors. So if it is equal to both of its neighbors, we cannot count it. And that is true for all these middle a's. For all these middle a's, each a has a couple of a's on its 2 sides. So they are all not falling into the criteria. Now, the terminal a's remain. About the terminal a's, I can say yes, they will follow. So the terminal 2a's will say yes, they have a at only one end. So this is true if we have only 2a's, then also both should be counted. If we have 5a's, then also only the terminal a's should be counted. Before that we have some other character or we don't have any character, doesn't matter. If you have 1a, then nothing can be counted. If you have 1a and before that some other character, let's say x, and after that y, then a cannot be counted. So this means that any block of the same character gives me 2 special characters. Any block of the same characters gives me 2 special characters, and that has no relation with another block. So whatever string I make, that string will have few characters, a block of same character, okay, a block of some x occurrences of one character, then another block of some y occurrences of another character, then another such block, then another such block, and so on. So each block can either give us 2 or 0. 2 if that length is greater than 1, 0 if that length is equal to 1, right? Which means that per block, if I take these possibilities, whatever I create, each such block will give me 2 or 0. So when I add them, again 2 or 0, again 2 or 0. So whatever damn string I create, when I add them, I will get, some of those blocks will contribute to, let's say L such blocks contribute to, so my answer will be 2 into L. That's it. Which means that it is not possible to create an odd number. Whatever damn string I create, it will be composed of some blocks, and each such blocks of same characters surrounded by not the same character. Such blocks will either contribute 2 characters or 0 characters, special characters, 2 special characters or 0 special characters, which means that my number of special characters in the string will always be a multiple of 2. And hence, if n is equal to something like 2k plus 1, that is an odd number, then we can clearly say no. That was my logic. So this entire thing I did. It took me a bit of time because I think I got confused with one or two cases, something like that. So you can see here. Yeah, okay, I solved it in 2 minutes. So even then, yeah, 2 minutes 55 seconds. And anyway, I was also careful; it should not go wrong. So anyway, this is how you can solve it. Let's look at the next question. So again, the yes case is within 50. Sorry, yeah, within 50. So at most 200 cases obeyed, and the no case is doesn't have any length kind of restriction. Yeah. So let's move to question number two. I took a bit of time in question number two. Let us see what problem two was. Array fix. You're given an integer array A of length n, and for any element which is at least 10, that is a two-digit number, you can break it basically. So it says you can delete it and instead insert the digits in the same order. That means you can break it. So for 12, you can break it into 1 and 2. Like 45, they have broken it. For 45, you can see over here, you have 45, so they have broken it into 4 and 5. Similarly, for 1, 2, you can break it into 1 and 2. I mean, so 12, 3, 45, 67. So we can do something like this. 12, 3, 45, 67. We can say we can break this 45 into 4 and 5 separate elements if we want. Now, after this breaking or not breaking, what do we have to do? So we can do this breaking any number of times. Now we have to transform the array such that the resulting array has elements in the non-decreasing order. They are all in this non-decreasing order. Now, this basically means over here I have this kind of possibilities. Like I can say 12 is greater than 3, but it should be less, the previous element should be less than the next element. So I think I can break 12. So I can do something like this: 1, 2, 3, then 45 and 67. This is in non-decreasing order. Similarly, you can also decide to split both these 12 and 45. What do you get? 1, 2, 3, 4, then 5, then 67. Both are correct answers. This is also correct, this is also correct. Both are correct. And but if you say, okay, I will break this 67 and this 12, then you will get 1, 2, 3, 45, 6 and 7. This is not correct. This is not correct. So if in some way you can get a non-decreasing order, your answer will be yes. If in any way you can basically split some strings, split some numbers, and you can get this. Okay, now the most interesting observation over here for me was this one. Each number is at max a two-digit number, which means that for the two-digit numbers, I have two possibilities. Either I keep them as they are, or I break them. So if I notice a 45 somewhere, I have two possibilities. Either I keep this as 45, or I break it into 4 and 5. Now, one thing that is clear from here is that a two-digit number, which is not having 0 in the tens place, so a two-digit number, basically a number greater than or equal to 10, is greater than any one-digit number. So if I say, okay, there is an array of two-digit number, one-digit number, whatever, there are some two-digit numbers. If I say that, okay, this particular two-digit number, I will have to split it. I'll have to split it. That means after splitting, they will become one-digit numbers. So if this was, let's say, 54, then they will become 5 and 4. If this is 45, this will become 4 and 5. Now, this tells you something that, okay, 54, should I ever split it? 54, I should never split, because if that gives me 5 and 4, that is a massacre right away. Because 5 and 4 are not in the right order. So, definitely I should not split it. But these observations, we can make tons of these observations in this problem, and we can try to optimize. But the thing is, I will again notice the constraints. The n goes up to 50. There are 1000 test cases, So up to I think n cube, anything is possible. Up to n cube, if I do it, it is still less than 10 to the power 6, so 10 to the, or even lesser I think, yeah. 10 to the power 5 into 2, so 50 cube basically gives me 125,000. 1.25 into 10 to the power 5, so multiplying this, it will become 1.25 into 10 to the power 8. So n cube is a bit more than 10 to the power 8, and n square is still, I mean, very well inside 10 to the power 8. So n square definitely is one approach I can follow. So I'll make some other observations. Let's say over here, you choose to split this 45. What does that mean? That means before this, there cannot be any two-digit numbers, right? If this you're splitting, if you're making this as one-digit numbers, that means the ones before them must be one-digit numbers. Must be one-digit numbers. If they're already one-digit numbers, very good. If they're not, you have to make them one-digit numbers. You have to split them. That's a must, because they have to be less than 4 or less than equal to 4. So you have if you're splitting this one, that means you're basically saying, okay, everything before this should be less than equal to 4. So whatever you're splitting, whatever two-digit number you're splitting, you will be making, I mean, the first digit will be at max 9. So everything before this has to be single digits. Each number has to be single digit. So now, this tells us that, okay, if I choose that, okay, I will split everything up to here, whatever are two-digit numbers up to here, that is one possibility. I can choose to split everything up to here. Is splitting everything always a good choice? No, this 54 is not a good choice. So if I look over here, let's say I had 12, 3, 54, 67. Definitely I cannot break this 54. Then 5 will come before 4, that is not possible. So the only way I have is 1, 2, 3, 54, 67. So not splitting always will give us the right answer. That's for sure. Now, what we have understood is if I'm splitting some I should split everything before I. So if I say, okay, then these are my possibilities, right? I split everything up to 0th index. I split everything up to index 1. I split everything up to index 2. I split everything up to index 3, and not others. Something like that. I split only up to index 3, only up to index 4, and so on. Only up to index n minus 1. These are my possibilities. And now I can say, okay, for each of them, I need to check whether that will give me a correct answer or not. Does it span all the possibilities? Yes. If I say that, okay, in the correct answer, whichever can build will give me an yes, let's say, that will have some last position as the splitting one. So that last position can be either before 0, that I'm not splitting anything, so we can have that no split, 0 to minus 1. This basically is no split. Okay, and then I'm saying that, okay, I will split up to index 0, I'll split up to index 1, and so on. If I split 0 to I, then I'll check, okay, by splitting 0 to I and not splitting I plus 1 to n minus 1, can we get the non-decreasing order? Can we get the non-decreasing order? So my claim is either the answer will be in one of these or the answer won't be there. Why so? Because there will be some last element which will require a splitting in some valid answer, some last element. Before that, everything you have to split. So that last element, whatever is it, if that last element is, let's say, 50, so then 0 to 50 should give me the answer. If that last index is, let's say, 50, last index. So whatever is that last index, that should fall in one of these categories. Now, how do you check this? For anything 0 to 2, let's say, or 0 to I, let's say, you basically do this. You just check going from left to right up to index I. You will just split and check whether things are matching or not, things are going in the increasing order or not. Let us see at the let's take a look at the code. My code. Yeah. Where is my code? There you go. So I was going in some wrong way, as I told you. I took the input and then I'm deciding what is my last. What is the last index I'm considering? So basically I'm saying that okay, last here basically says that up to last minus 1 I will split, and from last onwards I will not split, something like that. So I'm taking from 0 to n. N means I'll split all the numbers, and 0 means I will split none of them. So there are n plus 1 total possibilities if you think of it. Next, what am I doing? I'm basically saying okay, whichever you have to split, go very carefully. Split it. So this is your right digit, this is your left digit. So x is basically your ones digit, y is your tens digit. Okay, this selected thing is your tens digit. You will check, is the tens digit at all existent? If the tens digit exists, then only there is a point checking that. You don't split 0 8 to form 0 and 8. We will not do that. So we can split only numbers greater than equal to 10. So if it is not equal to 0, then only I am interested, otherwise I'll just ignore it. If it is not equal to 0, I will say, okay, whatever was the max till now. What was the max till now? Minus 1. For every last, I'm starting this. Are you less than that? So I'm starting with minus 1 because till now we have not seen anything. Now whatever I'm seeing, I'm ensuring that that is more than whatever I've seen before. So if the max is greater than this number, that means no hopes. Already the non-decreasing order has been broken. Okay, the max till now greater than y means already the non-decreasing order is broken. So continue means this last is not going to help us. So I'm continuing this v. Okay, I'm continuing with the next value of last. Next, max is equal to y in case max is not greater than y. So I will say okay, now this is your new max. Max is equal to y. Now the next step is x is definitely there. X you shouldn't check whether it is not equal to 0 or not. So the same thing, max is greater than x. If max greater than x, continue v. No questions here. It cannot be lesser. Max is equal to x. So up to that splitting point where you can split, that is your last minus 1, self-imposed splitting point. If there is a contradiction for this kind of a splitting, directly surrender. You can say something that since this splitting is failing, over here in this particular part, you can say that the next last values will anyway have these parts, will anyway go through these parts. So when I try the next last values, it will go through these parts once again. Right, because last is increasing, so I is only going to go from 0 to a greater value. So I will go through all these points, which means you can directly print a no. If you ever step into these if conditions, you can print a no directly and you can continue the extreme outer loop. That you can do. Okay, next, what else? I've come outside and I've said, okay, whatever you're not splitting, here be cautious. So whatever you're not splitting, later on in later iterations, you might be splitting them. So don't take an urgent decision here. If you're not splitting, then keep them upright and compare. If they are lesser than max, then you have no, you have to look for the next last. This needs splitting. This basically says that it needs splitting. Without splitting, this is basically, yeah, this or maybe its previous elements need splitting, something like that. So what I'm basically doing is for every last I'm doing this entire thing. So let's say last is basically a point before which I'm splitting everything and continuing through which I'm not splitting anything. And then I'm dividing that into two parts. Okay, these are the ones I'm splitting. These are the ones I'm not splitting. Then am I getting yes or no? If either one gives me yes, I will print yes. If any last gives me yes, if it comes out successfully. And continues are those statements which are saying, hey, I will not give you a yes in this particular thing. It will go to the next value of last. So continues basically take me to the next value of last. Got it? Okay, that's it. Next, problem C. Problem C I had solved in 13 minutes. You can see I still took more than problem D where I took 10 minutes. Problem C I took 13 minutes. So let us see what problem C is about. Arrow path. In brief, the problem is you are starting in 1 1 and you have to go up to 2 comma n, and you have to follow these arrows but in a special way. What is that? Every second these are the two actions that will happen one after another. What are the two actions? Firstly, the robot moves in one direction, and this is in our control. This is in our control. Sort of it says that whether the robot can reach the cell 2 comma n or not. This part is in our control. It can move one step left or right or down or up. Then, then it moves along the arrow that is placed in the current cell. Again one step. So every second the following two actions happen one after another. So let us see. The first example. Right, right, left, left, right, 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 left. Right, right, left, left, right, 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 left. What we saw is the first thing is our discretion. First step is our discretion. Second step is whatever is on current point. Whatever is on current point. So if you have on that current position, if you have right, it will move to the right. If you have left, it will move to the left. So what can I do over here? From here, I'm currently positioned over here. These steps will continue one after another. 1 and 2 will continue one after another. So first step 1, then step 2, then again step 1, then step 2, then again step 1, step 2. So step 1, I will mark using red, and step 2 I will mark using green. I'll make a copy in case we want to see other possibilities. Yeah. So first step, discretion. Discretion means I can move right or left or down or up. Now I cannot leave the grid that is mentioned over here. There are no arrows pointing outside the grid, and it can't try to go outside the grid and skip a move. Over here it is mentioned. It can't try to go outside the grid. So let us see. So it can move, let's say it can move over here, right. And then second step. Second step will happen, whatever is in that position. This position as right, so it will move to the right. This is not in your control. You have brought it here, so it will follow this particular thing, whatever is here. Got it? Next, you now have a discretion, so you can say, okay, I will bring it here, down. You could have brought it left also, right also. I'm bringing it down, and then it will follow. Second step, it will follow whatever is on current point, so it goes to the right because it is a right pointer. So you have reached the last one. So this is the correct way. Okay. The reds are basically what choices you made to figure out whether there is a way or not. So reds are basically, I mean, there you had options. After the red, you don't have option. You have to follow that ping. Let me show another way. Maybe let's say it will come over here. I mean, we can bring over here. Then the green will follow whatever pointer is there. So it will go to the right. Then I can say, okay, next you can move to the up. And then the green will follow whatever is over here and sit over here, right? Now, by sitting over there, it won't suddenly come back because next step is again our discretion. Next step, I can say, okay, if you come down, you can realize if I come down, then again it will go from here over here, so I'll win. But if I say go to the right, then this will take me to the left. And then if I say, okay, I've come to the left now, if I move to the down, yeah, from here it will move here. Yeah. Now, what insights do we get from here? So we have to say that these red arrows can be, is there a possibility of these red arrows? Green arrows are outside our discretion. So these red arrows can we control? Can we choose the step one, that is the red arrow, such that we can reach 2 comma n? Can we? So here always in this kind of questions, I step from the back. that let's say you have to reach here. Let's say you have to reach, let me make two others. Let's say you have to reach here. First of all, will you reach by a green step or by a red step? So from here to here, if you have to reach, you need one down step and so many right steps. Any other extra thing you take will be reverted. So basically, you need n minus 1 steps to the right and one step to the left or to the bottom. So basically, in total, you need n steps. Now, if your n is odd, then a red arrow can reach you to the last position. If n is even, then a green arrow can reach you. So we'll look at the question. The question tells that n is even, which means n is even basically means that the distance from the first cell to the last cell is even, which means only a green arrow can take me to the last position. Green arrow means that last move, which is a green arrow, will not be in my discretion. Okay, so what we understand is that that last arrow will follow some given pointer. It will, I mean, these given pointers basically. It will not be my own choice. So I will look at what given pointers can bring over here. I have two ways of entering the last position. In any kind of this kind of question, I do this kind of strategy. That okay, it can enter from the left or from the top. In the last move, can it enter from the top? No, because this position either has right or left. Nothing will take it to the bottom. So a green arrow, which will follow the pointers given, will not bring it from top to bottom. And so this particular possibility is gone, which means it has to come from the left. And from the left means this arrow must be right. There is no use taking it over there regardless of what is present over there. We know what is present over there because as it tells us, there are no arrows pointing outside the grid. So we know that it will always be a left arrow present there. But there is no use taking the, taking our position over there because it will not take us to our destination. So what we infer is over here there must be a right arrow for us to be able. If there is a left arrow over here, let's say if there is a left arrow over here, automatically I can say no. So this is a compulsory, right? This is a compulsory requirement. Necessary, but not a sufficient condition. Maybe you can't reach over here only. Everything to the left are basically left pointers. So this is important, but not required as of now. Okay. Now, the previous two positions, I mean, from these two positions, you can reach this this red position, right? From these two positions, you can reach this particular red position by your discretion. You have the power. So from there, how you come to this red position is not a big question because you have that power. You have that red arrow with you. That is a red step. Okay. So after this red step, you have the green step, which will happen automatically. But how you come over here is the main question. If you come over here, then you have one step. So basically, if you come, let's say over here, you come over here and then you come over here. Done. If you come to the top one, then you go down by your discretion and then you follow the arrow to the right, you are done. But step back. How do you come over here? For that, what do you need? So, to come over here, can I say, you definitely need this arrow. And to come over here, this particular position, can I say you definitely need this arrow? Right? And both are fine for me. From both of them, I can use my discretion to go to this particular second row penultimate element. So the thing is that both this A1 and A2, I can say, both this A1 and A2 are fine to me. and for that the elements before that, either of them needs to be a right pointer. Got it? So if I have both of them as left pointers, then what happens? From the left, whenever I come, it will always push me back. Now realize this thing, that as we discussed, let's say this is not in our discretion, this second point, whatever, I mean, this will follow whatever is in the current position. This is not our discretion. So basically, which are those current positions that uh, we need to depend on? Which are those pointers we need to depend on? This is one such pointer we have discussed. So this one is going to be the last move. What else? Before this, these two are basically a different parity. At these points we have the discretion, but at the points before them we don't have the discretion. So at these 2 points we don't have the discretion. And again, two before them we don't have the discretion. So over here I have the discretion. From here I can move it to the front. But so it will move alternately. In these two we won't have the discretion. If you pay attention, you will see, okay, from the beginning, the first point is our discretion. Then you step into a yellow, which is not our discretion. From there you step into a white, which is again our discretion. From there you step into a yellow, which is not our discretion, and so on. So these yellow things actually matter. These yellow things matter. What are there in this yellow actually matters. What are there in the whites, that doesn't matter. Only exception is this last one, except that you can get a pattern. So these are the yellows that matter actually. So these are the, I mean, we can draw for a larger thing as well. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here also you will say, okay, this position matters to me whether I can step to the right or not. To reach this position, this and this are our discretion. So before them, these two are again outside our discretion. And again, these two are outside our discretion. Then again, these two are outside our discretion. Then again, these two are outside our discretion. Then again, these two are outside our discretion. So can you see? The starting position always is in our discretion. Here we can choose. Here we can choose where we want to go to. And those yellow points are where we need to depend on those pointers. Now, what pointer values? That's the big question. Here we have seen, okay, here a right is a compulsory. Here what have we seen? If any of them is a right, it will help me get through. Any of them has to be a right. Either this one or this one. Or. How? If I'm located over here, I can step into this guy. Wait. I can step into this guy through that one. I can step into this guy through that one. So basically I can step into either of them. Let's say this guy through here also, through here also. And from here I can say, okay, take the discretionary, move to the next one and move over here. Which means that crossing this is a battle for me. Crossing each yellow thing is a battle for me. So the main challenge or the only challenge is cross every yellow wall. Right. So here any one of them, if there is a right pointer, I'm done. I'm happy. Next, over here. Let's say I'm over here. So let's say I'm over here or I'm over here, basically in these 2 points. Okay. I have to cross this battle. This is another battle for me. In whichever point I am. If I am over here, then this is the battle I want to cross. If I am over here, then this is the battle I want to cross. Right? So either way you can see that once again, if both are a left pointer, that is a problem for me. You see this? If both are a left pointer, so either I'm over here or I'm over here before this bracket, before this thing. If both are a left pointer, that is a problem for me. If either is a right pointer, I can move ahead. If either is a right pointer, I can move ahead and I can step into this white zone. At least, if not better into this white zone, I can at least move ahead. So here, either again has to be a right pointer. If both are left pointers, then I'll remain stuck over here between this and this. I'll just remain stuck. I can't move ahead, through that red wall. So this is how I'm moving it step by step. Again, if I see that, okay, over here also do we have that condition? So if I'm over here, yes, I need that kind of thing. I need to move either through, I can move either through there or I can move through there. So in that purple thing, one of them is needed. If I'm over here, either I move through this or I can move through this over there, something like that, which basically means that this one needs to be there, something like that. So that's the point. So I can say the only way to move past this particular purple bracket is that either of them contains the right pointer. If both of them contains left pointer, we can't move ahead. So these are some necessary conditions. Will that always solve my problem? Any bracket, let's say this bracket has some right pointer, let's say over here, you are over here. Now the question is, okay, this is left pointer, how can you move ahead? For that, this comes to the rescue. Okay, that is a left pointer, means this one has to be a right pointer. So you have the way to move over here. Which means that for every such diagonal thing, for every kind of white thing, you need something in your next yellow to provide you the space, to diffuse through that. So that is the condition basically that I used. That okay, all these marked areas, their or should be, either of them in the marked areas should be a right pointer. Again, I'm moving that here. Again, I'm drawing that here. Here, either of them at least have to be a right pointer. So all of these will actually, we will see that either has to be a right pointer. Similarly, going backwards here, and so on. So that's it. That is the necessary and sufficient condition, the way I see it. So, greedy algorithm, I would say a lot. Yes, there are DFS, shortest paths, all those things there. You can see BFS works, but this is a strategy that sort of, I think, should be working. So you can look at my solution. Yeah. So what it says is, what I've written over here is this. There's a small implementation, as you can see, it's a small algorithm. So from 1 to n minus 2, you have to be very careful with these extremes. And then I say, okay, if both are left pointers, AI, that is first array I and second array previous one, both are left pointers, means no, you can't proceed through that boundary. This is clear. That is a clear no. Okay, and similarly, if both these are left pointers, AI and BI plus 1, again no. So AI and BI minus 1 and BI plus 1, in this way for every AI I'm doing this. This is for A1, this is for A3, this is for A5, at the end for A n minus 3, right? N minus 3, yeah. Something like that. So I've done this, so check the A's and B's and check the A's and B's. If anywhere you see this kind of thing, print no. At the end, if you have reached the end, then just check this. B of n minus 2 must be a right pointer. Click on yes if so, otherwise no. Right? If the last one is not a right pointer, then there is no hope. So that again is, yeah, needed. So, next. So you can understand all of these are kind of greedy algorithms, so I'm not worrying much about the time limit. The time limit has to pass because this is a simple one iteration of the whole structure that I'm performing. Now problem D. This was a bit interesting. I would say luckily I just hit the right thing. While reading this problem, I had solved this problem in actually 10 minutes. Now, while reading this problem, at a point of time, I felt okay, what kind of thing? Rabin carp should not help here. KMP problems, etc. What can help? And thinking that basically, I felt okay, let me look at problem E. I opened problem E, I just looked at okay, graph problem, I'll come to it later. I stepped back, and suddenly things then came to my mind through some iterations, maybe. So let us see what this problem is about. It's a really interesting question. It says that a tandem repeat is a string of an even length such that first half is equal to second half. So if I take maybe ABCD, ABCD, that is such kind of a tandem repeat. So I can say ABCD, ABCD. This is a tandem repeat. Okay. Now, because the first half is exactly the same as the second half, so this is a tandem repeat. This problem's terminology, not a very universal terminology. Now, we are given a string with some question marks, lowercase Latin letters and question marks. So our goal is to replace each question mark with some lowercase Latin letter in such a way that the length of the longest substring is a tandem repeat. That is a tandem repeat is maximum possible. So length of the longest substring that is a tandem repeat is maximum possible. So we have to fill those question marks in such a way that uh, we have to create the longest tandem repeat substring. Substring basically means a continuous set of characters within a string. Contiguous, contiguously placed, whatever you say. Okay, the striking thing, the most important thing here was this particular thing, 5000. We all know Manager's algorithm, Rabin carp, KMP, they all work in, I mean, they are used so that they can help in linear time, something like that. The first time when I thought about this problem, what struck me, look at this code, and instead of forces, you don't have these 5 characters mentioned here. It gives you 10. So the substring, a substring of length 10 is a tandem repeat. Why? Because if you see this, CODE star 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 S. So we can fill it up in this way, SCODE. In this way, this first half and the second half are exactly the same. So this entire string basically is a tandem string, which is the best you can achieve. Tandem, what is that? Tandem repeat, yeah. So this is the best you can achieve. So somewhere what struck me basically is if I use Rabin carp. So basically a rolling hash kind of a thing if I use, what will I do for the question mark? So first thing I thought a bit, and Rabin carp was not interesting to me. I declined it because those question marks I can't assign something so that hashes will converge, so that the hashes converge. For example, if I have A, B, C star, and then after that if I have A star, C star, or A star, C, D, something like this. So what kind of algorithm will I apply so that these two, what kind of hashing will I apply so that these two will tell me the same thing? Um, Not very interesting because I have to say, okay, ignore this B and so on, which ultimately might mean a lot of computation for me. So this thing I have to ignore. KMP. KMP does an interesting thing. KMP basically keeps on maintaining that, okay, what is the shortest prefix with which this is matching? And that happens in a nested kind of a manner. Which means that if you have something like this, A, and then B, B, let's say, and then you have something like AACC, and then you have AABB, AACC, something like this. The thing is, not only for this guy it tells the correct value, that LPS which we say, not only for this guy it says the correct value, it also says a reasonably good, I mean it sends a good indication about this. It says that, okay, ending at U, this is a prefix that is also a suffix, AA. So this will tell me, this will give me the LPS value too. So somewhere basically, if I have question marks, that defeats a lot of things over here. A lot of the structure gets defeated because this tells me in a stairwise manner that, okay, if whole is not matching, go over there. If that entirety is not matching, go to a smaller thing. This is how this KMP works actually. And that is the first thing which struck me, okay, that thing should not work over here, because question marks sort of make the entire thing cluttered. Anything can replace my question marks. So KMP is the kind of structured algorithm that KMP is. I sort of had an immediate judgment that KMP is not going to work over here. You can think a bit maybe if you know these algorithms, but I sort of clearly eliminated it in my first few 10 to 20 seconds of thinking. Then what else? Managers can be used, but once again, uh, question marks bring the question. I mean, are the main question. Manager algorithm, if you see, it's a very good algorithm, a bit complicated algorithm. The main thing is if things don't hold that way, if question marks are creating ambiguity, is the ambiguity resolved by the algorithm? I don't think manager's algorithm has the potential to resolve that ambiguity. I'm interested to do the research, but for now I'll just keep that away, because while doing that investigation I sort of kept that away. And at the end I felt, okay, this will allow n square, where n is the size of the string. So let's think directly in that way. If I choose the first character, so if I say, okay, for every first character I will see what is the best that can be created, that creates a bit of a problem. That creates a bit of a problem. In basically extending from one case to another, I think I saw that problem. So the immediately next moment I felt the other way, that okay, the answer the answer can be basically maximum up to 5,000, which means that if I am saying some L length string will repeat, then this 2L can maximum be 5,000, which means that my L can maximum be 2,500. So if I say that, okay, for every L I will try, for every L is it matching or not, then something really strikes me. What? If I look at every 2L length string or substring, if I look at every 2L length substring, comparison is easy. How? I compare this with this, I compare this with this. The moment mismatch happens, break. Even if I compare the entire thing, what happens? This tells me whether in big O L time, this tells me whether it is matching or not. Now, do I have to do this for every 2L string? This is the thing where you can optimize. You can say, I will compare every string, every character. So look at this. This is your string, let's say. Now, let's say I will compare, if you decide that L will be my length. So I will say, okay, for 0, 0, 1, 2, 3, let's say L is equal to 4. Or let's say L equal to 3. 4, 5, 6, 7, 8. So I can say, okay, for 0, if it's of length 3, then this should match with this part, something like that. So if I start over here saying that, okay, let's stay in our second part. Am I matching with the 3 characters before me? Something like this. Am I matching with the 3 characters before me? I'll do the same thing for the next one. Am I matching for the 3 characters before me? Am I matching with the 3 characters before me? And so on. I'll keep on doing this. If I find 3 matches in a row, if I find L matches in a row, like over here, let's say I found L matches, or let's say something different. For here also I find it. For here also I find it. And for each of them I'm saying, okay, let's say this is a mismatch. This is not matching. This is matching. This is not matching. Sorry. Let's say this is matching. This is not matching. This is matching. This is matching. This is matching. Which means now the moment I see 3 matches in succession, I'm just matching characters. I'm just saying match ARI with ARI minus L. For the given L, I'm just matching this. I'm just seeing for every I, does ARI match with ARL? This kind of comparison I'm just forming. And then I'm saying, okay, do the match. The moment I find 3 consecutive matches, why 3? Basically L. L consecutive matches. If I find L consecutive matches, which is a simple carry forward technique for me, I will say, okay, the moment I see L consecutive matches, tick, yes, done. You have got the streak we wanted. So L is possible. We can say L is possible. Then we can try with L equal to 4. Now, with binary search, don't try this. Don't actually try in this way that, okay, if you can go up to 2500, so try binary search on this particular range, 1 to 2500, because binary search and answer won't work. You don't need over here, but if you want actually for tougher constraints, binary search and answer shouldn't work over here. Why? Because it's not a monotonic thing. If it works for L equal to 3, doesn't mean it will work for L equal to 2. Okay, so one example sort of can be, I mean, one example of this particular approach can be, let's say if you have this, for this particular example only I'll try to show, let's say A, B, C, let's see you have a question mark over here. You have a D over here, not matching. Let's see you have X over here, X, and this one matches, so what have I put there? I've put a C, so let's say we have a C over there. At 7 again we can have a question mark, and at 8 whatever we put. So we can, at the time of matching these characters, we can say either they should match or either is a question mark. So either they should exactly match or one of them is a question mark. That is the kind of thing I'm using for every I. For every I I'm finding this out. So these are my matching, not matching for every I whose I minus L exists. So I will take from L, basically I will take this so that I don't get array index out of bounds exception. And then yes, if I face continuous L number of matches, I'm done. That is a strategy which I basically used. So for every L I will do this. For every L from 1 to 5000 or 1 to 2500, I didn't discriminate. One thing that you can do is you can basically say I'll start from the last, that is 2500, and then where will I? We'll start from 2500, and then we will, the moment we get some match, the moment we say that L matches we have got, we will break. So that L is our answer. We can say that. The other thing is, yeah, go from the beginning. Whatever you get, that is going to be better than the previous ones. The last thing that you get, that is your answer. So that is the thing that I did. You can do either of them. So for every L, what am I doing? This particular approach. Start from L, go up to the end. For each character, see whether L characters before you that matches or you have a question mark in one of them. That means a match. If you have L consecutive matches, then L is a victory. So for some L you will have a victory, for some other L you will have a victory. So for L equal to 5 you might see a victory, for L equal to 7 you might see a victory, for L equal to 13 you might see a victory, L equal to 21 you might see a victory, and so on. So in this case, if this is your last one, then 21 is the best answer. So 21 gets 21 or 21 into 2, that is your answer. So 21 into 2 is your answer. Because a 21 length is sort of getting duplicated. Let us see my solution. It's exactly the same thing. I solved this thing in 10 minutes from the completion of previous program. So there you go. Same thing as I mentioned. I goes from 1 to n. So let us see this. Total length of the strings doesn't exceed 5000. So don't blindly put 5000, because then that will become a problem. Let me see if, again, with a bit of tension, let me see, have I put 5000 somewhere? No. If I put a 5000, that would have become a problem. What this says is that, okay, the sum of lengths doesn't cross 5000. If I put a 5000 every time, the loop will run 5000, probably 5000 into 5000 times, which means 25 into 10 to the power 6 times. And if the same thing runs 1000 times, I'll face TLE, time limit exceeded. So this is sometimes intentionally put in this way. Total length doesn't cross this. So up to n square, summation of n square will definitely stay within 25 into 10 to the power 6. But if you put this 5000 in your limits, in your limits basically, then that will create problems for you. So I put n, so basically this entire thing will run in n square, and sum of n square will definitely fall within the time limit. So I'm doing that exact thing if it matches. So for a certain I basically is your L, okay? For a certain L, that is I over here, we will run from that I to n, last index, and we will say that, okay, are you matching? If you are matching, then increase the streak from whatever the streak is, that is continuous matches. And if you're not matching, then streak is 0. So you have broken the streak. Now whatever is going to start, that is a new streak. So streak is 0. If streak is equal to I, that is this thing. If streak is equal to I, then the answer is equal to I into 2, continue V. You can say, why did I go up to n? Why not n by 2? I just felt, okay, n by 2, if n is odd, once again, a kind of edge case, etc. Who will think so much if suddenly an edge case comes and I'll fail over this? That's the reason I just kept, okay, go up to n. From a bit of experience, I know that it should not harm me. It will just take double the time, that's it. And double time should work. So, because 5000 square, basically, at the max, it is 25 into 10 to the power 6, which is far less than 10 to the power 10. So, n square is far less. N square should not be a big deal for us. That's it. So, we have conquered up to problem D. Now the turn for problem E, the last problem for this session. Okay, my mistake, first mistake while doing this problem was that this asks us to create a graph, and I felt it actually wants me to verify whether the given graph follows this thing or not, whether this given graph, I mean for a given graph, what is the minimum number of clicks, something like that. What this tells me is that I have to create a graph which will have the minimum number of clicks. What is this click? So basically we can add edge following this kind of condition. A clique basically is a subgraph where every node is connected to every other node. So something like this. This is a good topic of graph theory. Even in research of graph theory, you have this kind of things a bit. So let's say this is your graph. So if, let's say, these are all connected among themselves. Yeah, this basically means this is a clique. Now, let's say these two are connected in this way. This is again another clique. Why? Because every vertex in this part is connected to every other vertex. Now, these two parts may be connected in different ways. So, how many cliques do I have here? I mean, yeah, this is one clique. This is another clique. This is another clique. I have 3 cliques here, which have some overlaps, but all of them are not part of this, are not part of a clique. I can't say the entire thing is a clique because this is not directly connected to this node, so they cannot be part of the same clique. So much of my time actually got wasted in trying to think, okay, for a given graph, let's say for a graph where some edges are given, now how do you make those boundaries in such a way that you get the best clicks, you get the minimum number of clicks, you get the maximum number of congregations or clustering, whatever you call them. Whether that is possible or not, how to solve that is a different question. So let us take that differently. What this question says is that, okay, this is your criteria for forming edges. The more edges you form, the better it is for you, right? This is the criteria. So all AI should be distinct integers from 1 to n. You have to create a graph to be partitioned into the minimum possible number of clicks for the given values of n and k. Each vertex should belong to exactly 1 click. So over here, if I have to say, you cannot have this one then. So I can say, okay, this can be broken into these 2 clicks. So you can choose to have these edges and then these 2 will be the clicks. So basically, you have to cover them in some, basically those boundaries. There can be some overlapping edges in between, but basically you have to say, okay, this is something like click 1, this is something like click 2. So you have to say, okay, for these edges, you have to print at the end. So this is click 1, this is click 1, this is click 1, this is click 1. This is click 2, this is click 2, this is click 2, this is click 2. So these three are click 2. This one you can't say this is click 2 because the other vertices of click 2 won't be present there. But if this was connected to this and this, you could have taken that into click 1 also, click 2 also. That is up to you. Now, these AIs you can choose, but these AIs should be distinct integers from 1 to n. So what does it tell us? That an edge can exist if this holds. K is given and n is given. So if you have a point I and a point j, I you can assign some AI and j you can assign some AJ. Remember, AI's edges, they will all be distinct. From 1 to n, they will be in some arbitrary order assigned to all the vertices from 1 to n. Now how do you deal with them? So if you take this thing, when can this edge exist? If your difference in I and j plus your difference in AI and AJ is less than equal to the given k. Very complicated condition. But things become easy when you have to construct the graph. Then things are in your control. You have to construct the graph so that it is possible to divide into minimum number of cliques. Let's clarify with some example. So let's say it's 8 and 16. So let's say another example before that, 5 and 4. 5 and 4. 5 means you have these vertices 1, 2, 3, 4, 5. Now we can probably do in a number of ways. Let's say if I put in this way 1, 2, 3, 4, 5 AIs, let's say these are my AIs, then what I see is, okay, the way I is increasing, AI is also increasing. What does that mean? That means this summation will increase a lot from one I to another I. So if I see the difference between this, it is 3 minus 1 plus 3 minus 1, which is 4, which is within this, that is fine. So I can have it in this way. But from here to here, I will see that the difference is 4 minus 1 plus 4 minus 1. Okay? Difference between the I's plus difference between I's. These are my I's. Which means for this from 1 to 4 basically, it is going to be 6. 4 minus 1 plus 4 minus 1. So this is not going to hold, which means maximum this can be part of one clique. These three and these two. Let us see. The difference is 5 minus 4 and 5 minus 4. So this difference is good. We can have in one clique, both of them. Now, is it always the right way? Is this the best way? Let us try to understand. So for 1, 2, 3, 4, 5, 6, here, if I want to take them in the same clique, I want to minimize the sum. The sum or basically the differences between any two vertices. So if I put the AIs also in the same order, 1, 2, 3, 4, 5, 6, then between these two the difference is the maximum. If I put in the reverse order 6, 5, 4, 3, 2, 1, then also the difference between these two is the maximum. That is 6 minus 1 plus 6 minus 1. 6 minus 1 plus 6 minus 1 is equal to 10. Between any other two, it is far lesser. So can it be designed more intelligently? Can I say that with 6 vertices, can I get that difference lesser? Then what is my gain? If I can get this difference lesser, I can fit that within my required K and I can accommodate more. What this tells me is that, okay, with 6 numbers, you can fit that if the maximum difference allowed is up to 10. If K is 10, then you can have 6. But can't I have 6 for lower values like something like 8 or 7 or 6? Let us see. For that, we have to be a bit more diplomatic. So, one observation that we make is that from here to here, this difference is so much. This difference is also so much. So basically, if you are including for i's, if you're including 1, 2, 3, 4, 5, 6, already the difference between 1 and 6 is so much. Now, if I try to minimize this difference, the difference of AIs, can I say that is a good strategy? Because here this one is so much, between the others this one is not so much, difference in I's is not so much. So can I say, assign my AIs in such a way that wherever this one is high, this one should be low, and wherever this one is low, this one should be high, so that together they are within K. Right? So for AIs, this is one thing I can say, that if I plan something like this, let's say 3, and something like 4 over here, this is a very small distance, 3 and 4. And as a result of that, now my total difference between these two indices becomes 1 minus 6 plus 3 minus 4, which is 5 plus 1, that is 6. Now, when I look at this one and this one, my I difference decreases, so that difference can increase, my AI difference can increase by 1, with my total difference remaining the same. So the difference between 4 and 3 was 1, in this case it can be 2, so I will try with maybe the previous number, that is 2. Difference between 4 and 2. Here also, 2 minus 6, 2 minus 4, if you add both the absolute values, you get 4 plus 2 equal to 6. Right? How did it come? 2 minus 6 plus 2 minus 4 is equal to 6. Next, if I assign in the same with 1, 1 and 4, once again you will see this difference of the values is rising, and the difference between the positions is decreasing. This is a good strategy. What after this? After this we can say, okay, you have this 4 over here. Now you can have something like this, maybe a 6 over here. Why? Because I'm increasing in this direction, 4, 5, 6. What we saw is if I increase in this direction, then there is a problem. With this 4, the distance is going to increase, the AI difference is going to increase, so I'm coming in that way. So basically, this is a kind of, you can say, an intelligent kind of a strategy. What was my basic observation while doing this? My basic observation was that this difference is maximum, that is D. Then this difference is the next maximum, which is D minus 1. Then this difference is the next maximum, which is D minus 2. Then if I continue, this difference is smaller, D minus 3, D minus 4, something like this. The thing is, each has their own such kind of mechanisms. For these lower ones, this particular difference, maybe I'm not worried because they are not taking more than half the difference. This one will have the similar kind of demands. So one strategy that I had is, okay, if I say, give it the maximum value 6, among this the maximum value, and then bring from the end, bring the smallest value, so 1, 2, 3, 4, 5. Sorry, this again is a bad thing. 1, 2, 3, 4, 5. As a result of this, for this guy it is protected already. This guy is protected. So for this guy, the distance with any other vertex, that is del A plus del I, is going to be, for this particular thing, the del A plus del I is always going to be 6, if I'm not wrong. Yeah, with any other thing. But if I look immediately for the next one, let's say this one, with its next ones, what will I see? Once again the same problem. 1 to 5 and 2 to 6, both are the maximum. So the same problem is sort of coming up. Which sort of brought my mind, okay, now if I split into two halves, something like this, split into two halves, what benefit? First one gives me up to n by 2, then up to n. Now, this guy, whatever value AI it has, whatever value AI it has, what are the different possibilities over here? Maybe we can reach an interesting kind of a thing. I mean, we can reach different interesting kinds of things. What I'll be interested over here is that if I take by example, if I have some value like a 6, what is needed over here is I should have a very close value so that I don't suffer a lot. Something like a 5. Or let me take in terms of n. So if I have n, I should have n minus 1 over here. That preserves that thing. That is the best I can obtain. And the proof will actually be complicated if I understand correctly. Next step, what I can go ahead with that is that with this thing, there is absolutely nothing that this difference costs me. But the more non-uniformity I impose, the more problems I'll create for myself to actually verify the things. I can't have a 1 over here because the distance is so much. The distance itself is more than half. Okay, this can be a good way. That anything in this right half, let's say any x, from here the distance is going to be greater than equal to n by 2. So if here I am having the elements greater than n by 2, here I should not have elements, greater than n by 2 because, sorry, here I should, um, what did I do? If I have elements greater than n by 2, then that is fine, depending on what is the maximum I am creating as a result of that. So, okay, I'll maybe tell my strategy that I used over here. Maybe by chance I just reached it at that point of time. So it's basically up to n by 2, up to the middle mark, put also basically let's say n is equal to 10. Up to the middle mark, put 1/2 of 10 in an order something like this: 10, 9, 8, 7, 6. You can have the other way as well. And then, okay, it has to be the other way so that the difference is basically in control. 6, 7, 8, 9, 10. And I'll make a symmetrical arrangement, something like this. So 1, 2, 3, 4, 5. Why? Because then the difference between these two and the difference between these two will be the same. Is it? No. The difference, okay. So then the difference between these two will be 1. The difference between these two will be 3. And why is that interesting? Because the moment I go one step to the right, and the moment I go one step to the right, I am basically reducing the space by 2 overall. Which means on these two elements, the burden of my I factor will be 2 lesser because I'm coming 2 steps closer. Then next step I can say that okay, for these two, it will be, I mean the difference basically is 5, right? The difference is 5. Again 2 steps because I'm coming closer, so 2 burden is lesser. 2 burden is lesser over there, I'm using that 2 burden over here. And over here the burden finally is 9 and that part is 1. So as a result of this, what happened? With n equal to 10, I could bring all the 10 under k equal to 10. So for k equal to 10, up to 10 vertices I am able to keep together. Is it possible to have more than 10? Think this. So I think this is a better way to actually, sometimes in graph theory and many other such related areas we do this, that okay, it works, do you have a better solution? If you don't have a better solution, then okay, this is a strategy that you should employ. I think many proofs, even in research of graphs and other places, are based on this, that okay, if you have some result, establish it and prove that you cannot have a better result, then only you have the best result. So what I need to prove is that with k equal to 10, I cannot accommodate more than 10 vertices. Then this strategy works. So how can I show it? Let's say, okay, 11 vertices I will be employing. 1, 2, up to 11. Then the thing is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The difference in I and the difference in AI are the two things that I have to keep in mind. Here the difference in I will be 10. Can the difference in AI be 0? So difference between 1 and 11, the difference will be 10. Can the difference in AI be 0 between 1 and 10? No. It will be greater than 0, which means here only it gets violated. It will be at least 11, greater than equal to 11, which means k equal to 10 cannot accommodate 11 vertices. So k equal to 10, any k, with any k you can accommodate at most k vertices in a clique. K vertices in a clique. And my solution is actually going to give you k vertices. How? First, k by 2 integers. Sorry, let me write it in a different way. So first from k by 2 plus 1 up to n in ascending order, then 1 to k by 2 in ascending order. So that is one way in which you can get all the things. For a k equal to 5, let me show. So 1, 2, 3, 4, 5. You have 4, 5, or maybe 3, 4, 5. 3, 4, 5, 1, 2. The other way also should work. No, so in this case, if I show, then over here the difference basically is 4 plus 1, 3. 2 plus 3, 5. Same side, you don't need to worry much. Basically, the same side kind of thing. So 3 to 2, fine. I have a bit of look between these two. Yeah, this part is satisfying. This is a corner part. 4 minus 1 and 3 minus 2. So basically, this is satisfying. 5. Yeah, 5 should be the maximum. Similarly, if I look at this part, this is 3 plus 2, that is 5. So fine. The thing is, after you form this kind of a thing, that okay, you can form a clique in this particular way. This is my formula of a clique. This is my formula of a clique. This is how I will formulate a clique. Now, how do you form your cliques actually? Let's say you have n equal to 14 vertices, and let's say k is equal to 6. So the set, or basically 8, let's say. So the strategy is, in groups of 8, take them in one click. You can't have more than 8 vertices in one click. From here you know that. So if you have something like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So yeah. So I will first pick up the first 8 and I'll use that strategy above. So something like this, 5, 6, 7, 8, 1, 2, 3, 4. That's it. So what comes out of here? Here everything will be fine. This is one click. I'll assign the color something like this, 1, 1, 1, 1, 1, 1, 1, 1. This is, I mean, the click number basically. You have to print the click number. Then I will found this second thing, and here also I will do the similar thing. I can say, okay, there are 6 over here, so I can use a 6 kind of a thing over here, something like this. So 4, yeah, it will be 4, 5, 6, 1, 2, 3, but instead of 1 you will have 9 over here. So basically starting with 9. Right, so you can have 9, 10, 11, 12, 13, 14. Got it? And next you basically have something like this. These are all in click 2. I did exactly this. You can check my solution. So yeah, this showing why this problem actually works is quite mind-boggling, but I hope you got some insights. Chalo, what I have done is exactly this. I had some wrong notions, I reached some wrong conclusions, and that's why I found this extra x variable. And that time I thought it will be actually k by 2 or k by 2 plus 1, something like that. That was a initial mistake. Yes, I solved it in one go, but still, I mean, I did not submit a wrong answer because after writing the whole wrong code, the right cases came to my mind. So I did not have to submit the wrong code. So yeah, you can see that my answer number of clicks is going to be this. What is this? Basically n by x plus 1 if there is a remainder. So this is one way of writing that, n plus x minus 1 divided by x. Next, what have I done? For every index, I've done this, that fetch whatever number of elements are remaining from here up to the end. So either x you will take in one click, or the remaining elements, that is n minus I. Whatever is the minimum, that you will take in one click. Next, I've used this array, a very small array, keep in mind, not an array of length n. If I take an array of length n, that will be a nightmare. I mean, that will give me TLE. But I'm taking this kind of a thing. So y into x, if you do basically not x, y into n by x, that will give you n only. So overall we are using n space behind this and all the loops together, not an issue there. Then I'm using the C to fill up those blanks, that okay, these will be my things. This is useful for filling up this. Now I'm printing it just like that. So basically I'm forming it in this way. I'm first writing this 1, 2, 3, 4, then I'm writing this 5, 6, 7, 8, then I'm printing that in this way here. Similarly over here, I'm first writing this 9, 10, 11. Over here I'm writing this 9, 10, 11 from y by 2 to y. Then I'm writing the 12, 13, 14, 12, 13, 14, and then I'm coming down and printing everything. I'm coming down and printing everything. And then I'm going out and I'm saying, okay, print the answer. And what am I doing here? So for n, okay, this goes in x. So basically for every click, I'll print the same value, that is C, and then after that C plus plus something. So this is a click number. So 1 1 1 1, then 2 2 2 2, then 3 3 3 3, and so on. Got it. So implementations are easy. So educational round actually teaches you a lot of things, and hence it is very useful taking part in these contests. But again, this particular contest was more about mind-boggling competitive programming tricks, or not tricks, I would say rather intuition-based problem solving. So yes, maybe some good solving techniques have been used, but not very classical algorithms as such. Maybe the third problem I think was a bit of DP, or if you basically look back in the right way. If you work backwards, that's a good solving strategy. So always DP doesn't help. Sometimes good solving strategies like this, going in the right direction, helps you. And E definitely teaches you some aspects of graph theory. Not a very traditional question, but yeah, that's what it is. So I hope you found the session interesting, and this time I tried to actually create this lecture pretty soon when the contest finished. So I'm expecting a good rating increase. You can see these guys are uh, hoping some 88 increases in rating. Anyway, uh, see you all in the next contests. Take part in contests and come up to see the editorials. and I'll see if I can actually hold live sessions so that your doubts I can address, and then these sessions probably won't go so long. They will be totally centered around what your doubts are. So yeah, see you, take care, keep coding, and please share with folks who you find might find this informative. So yeah, see you all in the next videos. Bye. Good night. Goodbye.